All right, good morning, everyone. My name is Gillian. I am a firmware engineer at Nordic Semiconductor, and I'm super excited to be here today to talk about taking a data-driven approach to Bluetooth LE development. Instead of guessing about how your devices are performing in the field, we actually want to collect data in the field to inform different connection parameters and measure the stability of our system. With that, let's look at exactly what we'll be touching on today. I'm going to start with a discussion around throughput. Throughput is an important factor to keep in mind when it comes to power optimization. We'll look more specifically then at the peripheral power efficiency trade-off with latency. And then, when things go wrong in the field, we also want an understanding of not only our baseline stability, but also what kind of pieces of information will help us with debugging those issues. And then finally, I'll wrap up with some practical application. How can we actually leverage some open source supplies? So the Zephyr API in particular for Bluetooth has got some really rich information that we can get through various callbacks. And then I'll walk through an end-to-end system that is reporting some of this data. And then wrap up with some resources that you can look at if you want to dive into these topics further. But first, a little bit about me. I am a firmware engineer. Before joining Nordic, I was working in the defense and space industry and really got an understanding of firmware development, but got interested in how do we scale these systems, how do we scale firmware. So I joined Memfault in 2023, and since then I've worked and had the privilege of working with a number of different IoT companies to help them ship more reliable products. This past summer, Memfault was acquired by Nordic, so I'm now working with some incredible people at Nordic Semiconductor, and really enjoying that transition and that learning opportunity. I am based in New York City, so if you're also dealing with travel plans, I understand with some of the changes in flights, so I sympathize. All right, let's look at, first of all, some framing around the kind of conversation we're going to have today. So notably, we'll be talking about optimizing the peripheral, this downstream peripheral, let's say a wearable system that is connected to a central. This is a less power constrained system. It might also be running a battery, but we're less worried about optimizing on that end. And we'll be focused on the connected state, in particular, connection parameters. And advertising is also a very interesting dynamic that we could look at, but we're going to focus on that connected state. First, we'll look at the throughput. Throughput's very important when it comes to power efficiency. We want to optimize our throughput because the longer that we are sending data, the longer our radio is on. So increasing that efficiency of our data transmission is going to help us with optimizing our peripheral power. So you might be thinking, if you're familiar with a Bluetooth stack, is it just about the PHY data rate? In fact, there's some other factors at play here. In particular, overhead is a main factor. We have a lot of different fields in these various layers that will add overhead and increase the amount of data that we need to be sending across this link. We also have ACKs and something called the interframe space that will add additional delays for good reason, as adds to the robustness of the Bluetooth protocol, but is going to impact the observed throughput. And then finally, we have some varying max payload sizes. So that's a aspect that we're going to be focusing on a lot today as well. But let's take a look at each of these layers and see how the throughput is impacted at each of these layers. To start off with the link layer. At the link layer, we have about a third of our packet that is used for overhead, and then about 27 byte max payload out of 41 is our actually useful data. If we were to calculate the throughput at this layer, we have the efficiency of this packet is the time to transmit those raw application data bytes over the full packet time. So that's going to include the frame space, interframe space, and those ACKs that we're performing. And then we multiply that by our PHY data rate, and that gives us the throughput at this layer. That's not the full story, though. We want to go up another layer and see how else our throughput is being affected. At the L2 cap layer, We are still constrained by this 27-byte max payload, but we do have additional overhead here, 4 bytes for this payload. Note this payload is able to span multiple link layer packets, but we still are constrained by that underlying max payload size. So let's build to kind of this culmination here on where we really want to see some data collection that we can do. And that's going to be at the at layer. This is where we're performing GAT operations. So we see at this layer that we have something called the at maximum transmission unit. This is a parameter that we'll be able to negotiate with our central up to 512 bytes. By default, it's 23, and that's a parameter that we want to try to push beyond that default value. If we look at some actual numbers related to this and actually seeing how various numbers increasing that MCU size affects the throughput, we start with that 23 default bytes, and we can see our observed throughput is at this 226 kbps. So this is using some numbers that you can dive into a little more deeply into an article that my colleague has written about this. But we're looking at 226. If we go up to the iOS 10 max, so this was one of the resources that I was looking at that had this value, 185 would give us 294, so that's a nice jump there in observed throughput. And then if we go up all the way to that max, we have 300, we see a throughput of 301. We do have a diminishing return here, and that's because we're constrained by that link layer max payload size. So there are some optimizations that we can, some optimizations to throughput that have been made through various key revisions in the Bluetooth stack. Before I go on to that, I will mention like the general equation that we can use here is similar to previously. We have the link layer throughput times the efficiency of this packet. So that's our MTU size minus the overhead. So that's our actual application data over the overall packet size. So looking at those key revisions, if you're familiar with the Bluetooth spec, you might be thinking, okay, yeah, there's more to the story here. We also have the LE data packet length extension, which is a huge improvement on that packet payload size. So we go all the way up to 500 or 251 bytes, and that takes our data transmission up to like 2x from our baseline. If we on top of that add the revision, the LE2M5, so that takes us to a symbol rate of 200 megabits per second, megabytes per second, then we can see a 4x improvement. Finally, one other revision that does have an impact on throughput is actually a revision that allows for extended range. So that is important for applications where you're working in a larger area and you need an extended range. That is at the cost of speed, so that will affect our throughput because we're encoding one bit with multiple symbols. So that's something to keep in mind if you're working in that kind of space. There is varied support across the ecosystem for these features. So that's something to keep in mind here. We want to make sure that if we're wanting to take advantage of these different revisions, that we're aware of how that's supported with the central that we're talking to and the other peers that we're talking to. With that, let's look more directly at actually the power and latency trade-off. So that's an important aspect for Bluetooth LE development. And we'll look at the connection parameters that we can tune associated with this. To start off, we'll look at the connection interval. So this is the opportunity to exchange data at the time between those opportunities. The range is 7.5 milliseconds to 4 seconds. And actually, in fact, there's been a revision in the 6.2 Bluetooth spec to lower that minimum. So for even higher applications where latency is very, very important and you want low latency, there's now support for that, which is really cool. But to note here, that does have an impact on our peripheral power. So the longer our radio is on our peripheral, so how frequently are we waking up, that's going to have an impact on our peripheral power efficiency. So I have a brief diagram here on kind of that setup. So we'll have a connection event where there's a peripheral wants to transmit data. It does that, then turns back off for that period of time until the next connection event. What if we wanted to have a increased power efficiency without that trade-off with latency? There's a really, some of you might be familiar, there's a really interesting concept called the peripheral latency, or the connection event subrating, which extends this concept where the peripheral power can be optimized by turning off the radio by skipping these various connection events. So we see in this diagram, these vertical bars are our connection events, and we can skip 0 to 500 of them. And then at the very end of our window of transmission, it's called our supervision timeout, we can transmit data if we need to. This does enable significant power saving, so we do want to take advantage of this where we can, if it's possible for application. No, I have a note here on the minimum of 6 connection events at the end. So before the end of what's called the supervision timeout, we were required to maintain that connection by waking up before the end of that supervision timeout. This is the time, so as a summary, this is the time allowed without synchronization before that connection is considered lost. So we could be calculating our supervision timeout to be too short. If it's too short, that could mean that our peripheral is not able to exchange data. And when it goes to, there's spurious disconnects. So if we disconnect too early, then that could mean that the peripheral will not wake up. If we have too long of a supervision timeout, then we might see that our device is not able to search for this connection properly. There is a general equation that we look at for the minimum here. So peripheral latency plus 6 connection events is the recommended value for accounting for retransmissions. And we multiply that by our connection interval. So summarize, we don't want too short of a supervision timeout such that we would have spurious disconnects. But if our supervision timeout is too long, then our peripheral is going to be searching far beyond the time by which it should have disconnected. So the radio will be on for much longer than we would expect and we would want for this application. So looking at a higher level, generally when it comes to stability and debugging issues, there are a number of key points that we may want to collect that will inform us not only of the stability of our product, but also how can we narrow down exactly where the issue lies. There are a few categories of information that I'm highlighting here today. The first is around kind of characterizing that stability. So how often are disconnects happening? If we have access to a disconnection callback, then we can count the number of disconnections that are happening. In my experience working with companies, a counter metric is often very, very powerful. So this alone is really, really great to have on hand. Additionally, what's the ratio of failures to successes on our device for transmitting data? That can give us a sense of overall how stable is this connection, and how that might be changing between releases of our firmware. Finally, are there crashes on the device? If we know there's crashes, if you know there's unexpected events on the device, then we can know if we're working with maybe a clean disconnection versus the device just crashing. So isolating that issue and having that additional data will help us there. What will be really nice as well is to know what our peer is exactly. What is the manufacturer of that device? Additionally, what is the link layer that we're working with there? And then this is important for understanding the exact device we're working with, because there will be various support in those stacks for those additional features. So that will help with our power optimization that we want to do here in regards to throughput especially. And then finally, environmental factors. This is always going to be something we talk about in embedded systems. Are there poor RF conditions? Knowing if we're working with a unstable environment or an environment with a lot of interference. is going to help us narrow down that issue. There's also an interesting aspect that I learned about recently. If there's multiple peers that are bonded, that can have an impact as well. So there's a limited amount of storage available for bonds, and if there are too many, then we can see unexpected disconnects. So that's something that we can collect as well on the device. In terms of how we practically apply these concepts, we can actually leverage the Zephyr Bluetooth connection callbacks. So I'll highlight, if you're in a Zephyr application, this is a really nice feature that's available to you. With a connection, we can register callbacks, notably the connected, disconnected callbacks. So in that connected callback, we can capture data about that connection. And then in the disconnected callback, we can count those disconnections. We can get some information on why disconnected, and so forth. And then we can also get our remote information, peer data on the manufacturer and the link layer version that we're working with. We could also request the features supported on that device. And then we can also get notifications if our parameters update. So if our central negotiates a different value, we can be notified of that, and we can record that value in these LE param updated and LE data length updated callbacks. So it's a handy macro in the Zephyr Bluetooth stack for registering those callbacks that I've shown here. And then within those callbacks, we can use several different functions here to get that information. So Bluetooth connection get info, notably, and then we've got the remote info getting the MTU that we have with this connection. And then we can also register commands or submit commands to HCI to get even further data about our connection. I have simplified some of the code for these slides, so definitely take a look at the Zephyr source for complete information. First, we're going to be looking at the Bluetooth connection infrastructure, and specifically within this, we have a number of high-level pieces of data about this connection, so the type, the role, and then the connection state and security-specific info. However, we're going to be focusing on, for this discussion, the Bluetooth connection LE infrastructure, because that has information about our LE connection. So we see some familiar values here. The interval, this is the connection interval that we're working with. We also have the connection peripheral latency, so that'll tell us if we've been able to establish a peripheral latency that will enable that power efficiency. And we also get the supervision timeout. So we can collect this data about each of our connections and then do comparison across various parameters if we're adjusting these within different segments of our fleet. Next, we'll take a look at this additional connection information structure we have on data length. So this is going to be our link layer, transmission payload, maximum size. So we actually capture in Zephyr the TX and RX values. So this will tell us if we have that data length encoding optimization or revision enabled in our peer, and if we're able to take advantage of that. Finally, we'll take a look at the remote information that we're able to see with the peer that we're talking to. So this is, like I mentioned earlier, the manufacturer, and the per manufacturer unique revision. So that might be registered if there's additional revision numbers we want to know for this device. And then we can also get the link layer version here. So a lot of information. I didn't cover everything that is available through this Bluetooth API, but there's definitely a lot in there. So yeah, I would definitely recommend if you're in a Zephyr application to take a look at what else is available. Let's take a look at an end-to-end example. I have some specific technologies mentioned here, but this can be generalized to whatever backend, gateway, and system you're working with. So I have an example data that I'll be showing off that was collected on an NRF52 L15 DK running a Zephyr application. We're using Memfault SDK, which is a product that I work on, for collecting observability data. So it's collecting data using those callbacks, and then sending it over using a GAT service, the Memfault diagnostic service. This data is then being streamed through a iOS app. There's also an Android app. So this could be an Android or iOS device. I just have an iPhone. And that's leveraging an HTTPS API to push data up to a cloud system. I have my West build command here. So if anyone wants to try out using this sample app that I have from the SDK, that's available here for your reference. Let's look at this device operating and kind of how data gets transmitted up to the cloud. First, we start advertising when the device boots up. We are able to, in the mobile app, see all the devices available. We scan for the devices, select the one that matches, and then we're able to establish a connection. So we see that reflected in both the application and in the mobile app. And then we're able to trigger a heartbeat, which is a unit of data. So that will be essentially serializing or capturing all of the data we have already collected through those callbacks when we did that connection event. And then finally, we have the data getting pulled up through this application, and that's getting posted to our cloud. So let's take a look at what ends up in our cloud system. So we see some of these values that we talked about. We have our connection interval, we have, which is in microseconds, and then we have the peripheral latency. So actually, it turns out that for this application, we had a peripheral latency of 0, so if we wanted to optimize this further, we could increase that value and optimize the radio on time there. We got a supervision timeout of 420 milliseconds, so that value is in units of 10 milliseconds. You want to watch out for units here because it varies across Zephyr versions. And then we also captured the LE data. We saw that we have the LE data packet length extension enabled here, which is really cool. So that was really fun to see. And then additionally, we get the GAT MTU size, which for my phone, which is iOS 26, this actually supported a higher MTU than the previous iOS version reference that I was looking at for this. So that's really neat and fun to see that we actually are using a higher MTU than we had before. And finally, we see some information about our peer. So it's on an Apple phone. So I can see Apple represented here, and that's decoded from this remote information. There's public data on what that encoding is for manufacturers. So we're able to decode that, and then we can also see our link layer version. So we're on link layer version 6. Finally, when it comes to actually aggregating this data, an example of, say, we're collecting some sync success data. I have some simulated data for a large fleet here. We can see comparisons across segments of our devices. So in this case, I'm looking at version information. So I'm seeing that the sync success rate of my Bluetooth connection is decreasing when I've shipped a different version of my firmware. So I can see that compared across these different segments. We could also extrapolate that to different segments of devices. So say I adjust a various connection parameter or some of my throughput optimizations. Then I can see that, we could potentially see that change between these different groups of devices. If we want to inspect exactly what's going on with this data, it would be great to click in and be able to look more closely. I am highlighting here as well. Collecting battery data is very powerful as well. So what we can do is we could collect the state of charge drop over that period of time, over that connection, and I could see exactly how much power is being used for that connection. And then I could leverage that as some aggregation of that as well to understand the power output here. I noted earlier that collecting crashes is really valuable as well, knowing if that might be related to our stability. So I highlighted the metrics we're working with here. We saw a increase in sync failures for this device. I could inspect the crash data and investigate that. So this might be correlated. When we click into a crash, that might tell us at an exact line of code, what is going on. So this could be either related to our Bluetooth service. In this case, we had an error in our GATS protocol, in our GATS service, excuse me, and that's attributed to some failure to allocate memory. But it could also be completely unrelated to our Bluetooth connection. In which case, the user sees the same thing, but the root cause is different. And as an engineer, you really want to know that. All right, if you want to see some more information about this, I have a few references here. I spent some time reading the developer handbook, which is a really fantastic reference if you haven't read that already. We have a few articles on one of the blogs that I help out with. There's some practical information on getting started, and then throughput discussion as well, related to what I started off with. And then finally, if you want to look at the source code that I referenced here, the Bluetooth connection information is public, of course, and you can look at that. I linked the header here as well. And then finally, if you want to see an example of leveraging these callbacks and how to use this in your application, I have an example linked in the SDK that I used for the application. Thank you so much.